A very warm afternoon to all of you. Myself, Neetu Chandravadia, PhD scholar from the Department of Physics, Saurashtra University, welcomes you all on this platform named Vigyan Yatra, a travel for scientific Indian minds towards Vikshit Bharat. Vigyan Yatra is a series of conferences session for March 4th to March 15th, 2024 and is jointly organized by the Department of Physics, Saurashtra University, Rajkot, Vigyan Gurjari, Gujarat Prant of Vigyan Bharati, VIBHA, and GUJCOST, the Department of Science and Technology, DST, under Gujarat Vigyan Sammelan. We are honored to have with us Professor G.C. Bhimani, Dean, Faculty of Science of Saurashtra University, Rajkot. We have a special guest among us, Dr. Arvind C. Ranade, Director of National Innovation Foundation and National Secretary, Vigyan Bharati, VIBHA. Shri Jignesh Borisagarji, Secretary of Vigyan Gurjari, Gujarat Prant, and Executive Engineer at Gujarat Power Research and Development Centre, GPRD, at Government of Gujarat, Gandhinagar. We are extremely grateful to our patrons and co-patrons, Professor Nilambari Dave, Honorable Vice Chancellor, Saurashtra University, Professor Chaitanya Joshi, President of Vigyan Gurjari, Gujarat Prant, Dr. Narottam Sahu, Honorable Advisor and Member, Secretary at GUJCOST, Gandhinagar, Dr. R.G. Parmar, Registrar at Saurashtra University, Rajkot. I also welcome Professor Nikesh Shah, Head of the Department at Department of Physics, Saurashtra University, Professor P.N. Joshi, Secretary Vigyan Gurjari, Gujarat Prant, Rajkot, Professor J.A. Bhalodia, Dr. Piyush Solanki, Professor H.O. Jethwa, and Dr. David Drew, sir. All of these are the staff at Department of Physics, Saurashtra University. Moving ahead, I please request David Drew, sir, to kindly welcome and introduce Professor G.C. Bhimani, sir, for his opening remarks.
Namaskar. Today, sessions on the Vigyan Yatra, day 2. We have started on the yesterday and we are going on the travel of our scientific interest to the Vikshit Bharat. In this traveling, I am very happy to inviting as well as welcoming all the dignitaries, co-patrons, patrons, and chief patrons of the session. As well as I would like to invite the invited speaker, the Dr. Sudhindra sir, as well as Mr. Ramcharan Meena sir. Today, with us in a co-patron, I would like to introduce Dr. Arvind C. Ranade sir. He has completed his MSc Master's in Science as well as doctor degree from the Astronomy IUCA in Pune 2008. He is renewable scientist at Vigyan Prasad Department of Science and Technology, as well as he has started his journey and taking a lot of awards and awardees on the Lilabai Putkar Award in 2000, Acharya Shri Award in 2013, Vigyan Puraskar in 2017. He is also served as a registrar at Vigyan Prasad and he is executive director of Indian National Science Academy. I would like to welcoming Honorable Professor Girish Bhimani sir. He is a professor and head of Department of Statistics, Saurashtra University. He serves a lot of roles in the Saurashtra University, such as a member of syndicate, member of Senate, and he is also served as a member of Academic Council of Saurashtra University. He is served as a Dean of Faculties of Science of Saurashtra University. He is a Chairman of Saurashtra University Central Admission Board, as well as furthermore Director of Center for Social Executive and Inclusive Policy of Saurashtra University. He is also serves as Director of IQSC Cell and he is a member of Academic and Administrative Audit. He also serves as a formal Vice Chancellor of Saurashtra University, Rajkot. I welcome you all of you and it is a very great time to talk about the Vigyan and about the Vikshit Vigyan. As we have learned from the Atharvaved that the Atharvaved said that the Tom Gyanam Vigyanamasi. It means that we have Gnan, Gnan. At that time we have used Vigyan for the society and for the betterment of the society. So I welcoming all and thank you be present here. Now I am welcoming Dr. Arvind Sianade sir to give his uh, valuable words to the Vigyan Yatra.
Thank you, sir. Am I audible?
Yeah, audible, sir, please.
Thank you. Thank you so much. Uh, First of all, I really have a lot of compliments to Vigyan Gurjari, Saurashtra, Prant, especially Professor Nikesh Saha, who is the president of Vigyan Gurjari, Saurashtra. I also extend my thanks to Vice Chancellor of Saurashtra University, respected Ma'am Nilambari Dave, Professor Chaitanya Joshi, who is a president of Vigyan Gurjari in Gujarat. This program is getting organized in association with GUJCOST and Dr. Narottam Sahu. He has also been a very good friend of mine. All the faculties, dean, and the registrar, everybody who is associated with the Vigyan Gurjari. I compliment Vigyan Gurjari for very beautifully and thoughtfully organizing Vigyan Yatra, which is a travel for scientific Indian minds towards the Vikshit Bharat. When addressing to a very intellectual class of the country who is very well convinced about what is the potential in the science and technology when any nation comes for the developmental or related activities wherein we would like the Bharat should be developed by 2047. And in the process, it becomes important for all of us, especially the people who are nurturing, who are shaping the young minds and trying to make them realize the potential of the work that they can carry out, especially with the tools of science and technology. So it becomes important for the organization like Vigyan Bharati, who is motivated, who has been inspired with the philosophy of a Swadeshi science movement. Especially all the people who are presently listening to me, you all will agree to me saying that when it comes to the subject of science, we always consider Vigyan or science is a boundaryless, which we actually cannot consider something called a Swadeshi or something called Pardeshi. But the fact of the matter remains very important when it comes to the very highly cultured, highly traditional knowledge-based society like an Bharat, which has got huge amount of repositories of knowledge in terms of the various knowledge resources when it comes to the yoga, when it comes to the Ayurveda, which perhaps have always remained a source of inspiration when it comes to the living standard, how one has to live with the peace of mind, making our heart and mind to be cool, calm, at the same time, very balanced. And I think when it comes to the such very vibrant topics and trying to understand the consciousness of the mind, then I think India is the only civilization or the Indus Valley civilization for which we all really feel proud, has got a tremendous amount of, you know, what you call is a knowledge resource, which takes us, which tells us, which make us realize that in the progress of science, if we try to make it a part and parcel of understanding the science in a very systematic way, wherein we call it as the science and spirituality, then the constructive outcome is bound to come. So for making that science and technology to be a fruitful for the humanity, then a culture also carries an important you know I would say the parameter. And in that particular philosophical idea, the Vigyan Gurjari, he's been working. And when it comes to the talking about the science available in our regional, kind of a domain, because India is being such a, different kind of a culture, different kind of language, and all repository knowledge which is stored in the different part of the country. It becomes so important that we need to not only nurture, but we need to understand, identify, and take it further. So the program like Gujarat Vigyan Sammelan also plays a very significant role. And I think in the context of national education policy, these are all become so important. And I really compliment for Vigyan Gurjari, making it realize and understand the potential of the regional language, the knowledge repository, the impactful work that has been carried out. We all are the people who really believe that science and technology has a potential to really move towards the developed nation with the help of the tools and techniques that we have. And especially on this occasion, when we celebrate the National Science Day, there is a indigenous technology also becomes important. And I really feel that today the two speakers who are going to speak us, who is going to give us the idea, especially in terms of the modern science, how the various tools and techniques are available in terms of the science becomes important when we really try to understand the materials to the context of its utility. So characterization of material equally becomes important, and on which Dr. Sudhirendraji is also going to speak about, who is coming from the BARC Mumbai. And at the equally, we are also going to listen to Shri Ramcharan Meena, who is going to speak about the various facilities at Inter-University Accelerator Center. So when we try to decide that we have to make the nation proud, we have to make the nation develop, this becomes important tools and techniques that the youngsters should be aware of and try to make use of these tools and techniques, so that ultimately with the help of these modern techniques and technology, how can we make use of such tools and techniques for the benefit of the common people? I think this series of talk is actually fulfilling the idea of what is to be done and how it is to be done when we have a very young, bright minds in front of us, when we speak about the demographic dividend, and especially at the right time, we really nurture such minds and try to motivate and convert that into the constructive ideas, where the tools and technique learned during this period can be utilized in a very constructive way. So I think on this occasion, when the Vigyan Gurjari has planned a Vigyan Yatra, which is having a series of talks started from yesterday and is going to be there till the 15th of March, I'm sure the compilation of all these summaries of this talk will definitely give the good amount of knowledge resource, especially to the young minds. And I feel that because speaking very long will is not something that is desired, but it is very important that when the speakers are going to speak about the modern tools and technique, especially the today's two speakers are going to speak on this, it becomes an important for the youngsters to realize that how this modern science can actually be utilized, provided we really understands this for the benefit of the humankind. And I consider that this is one of the way of making the young minds to aware about the tools and techniques, how that they can be consider this area of physics is an important, when it comes to the ultimate service to the nation. So on this occasion, I really thanks to the organizer, to the president of the Prant unit, all the organizing team from the different part of the Gujarat. At the same time, the people, I also got to know that there are half of the people who have registered for this Vigyan Yatra are also coming outside the Gujarat. So it is important that this knowledge repository does not limit only to the Gujarat, but also going beyond, which will take a lot of benefit out of this Vigyan Yatra series. And we look forward to have a very constructive outcome of this series. With this, thank you so much for everyone. And I am also eagerly going to listen to the various talks by the two different speakers today. And I convey my best wishes to the organizers as well as the speakers. Thank you. Dhanyavad. Namaskar.
Thank you so much, Ranade sir, for your consequential words. Now may I please request Professor G.C. Bhimani sir to deliver the opening remarks for the session today.
सबको नमस्कार। जैसे कहा जाता है, देश मेरा बदल रहा है। जब मेरा देश बदल रहा है तो आप सबको भली भांति पता ही होगा, जब इस देश में नेतृत्व किया था G20 देशों का, तब देश के प्रधानमंत्री ने जो पत्रिकाएं छपवाई थी, उस पत्रिका में बहुत सूझबूझ के साथ लिखा गया, प्रेसिडेंट ऑफ भारत, इंडिया नहीं लिखा गया। क्यों नहीं लिखा गया? क्यों कि ये उसी वक्त देश के प्रधानमंत्री ने बताया था कि ये मेरा देश अभी विकसित भारत होने जा रहा है। दोस्तों और मेरे साथ जुड़े हुए सभी वैज्ञानिकों, ये जो विज्ञान यात्रा है, ये विज्ञान यात्रा जैसे अरविंद जी ने बताया कि ट्रैवल ऑफ साइंटिफिक इंडियन माइंड्स टुवर्ड्स द विकसित भारत, कहीं न कहीं हर कोई जो विज्ञान के क्षेत्र में काम करते हैं, हर कोई के लिए ये विकसित भारत में उनका योगदान रहे, इसीलिए तो ये गुजरात प्रांत के विज्ञान गुर्जरी का ऐसा एक विज्ञान यात्रा शुरू की गई है। ऐसे में गुजरात प्रांत के बोरी सागर जी को मैं बहुत बहुत बधाई देता हूं, और साथ ही में हमारे राजकोट के और सौराष्ट्र के जोशी जी जो प्रांत संभाल रहे हैं। कहीं किसी के मन में सवाल भी होगा कि ये गुजरात प्रांत और ये सौराष्ट्र प्रांत वो कैसे अलग हुआ? ऐसे अलग नहीं हुआ है। गुजरात प्रांत ये गुजरात की साइड, दक्षिण गुजरात मतलब साउथ गुजरात, मध्य गुजरात और उत्तर गुजरात देख रहा है, और सौराष्ट्र प्रांत जो है वो सौराष्ट्र और कच्छ देख रहा है। तो हमारे जोशी जी को भी मैं बहुत बहुत बधाई दूंगा। जैसे बताया गया कि आज के दिन डॉक्टर सुधींद्र और डॉक्टर रामचंद्रन मीणा जी जो बताने वाले हैं, उनसे मैं ये समझता हूं कि ये दोनों साइंटिस्ट है। एक साइंटिस्ट बाबा रिसर्च एटॉमिक सेंटर यानी बोला जाए तो BARC में है, और दूसरे है IIC नई दिल्ली में। वो जो कहेंगे वो बात हम युवाओं को बहुत न बहुत सोच समझकर अपने देश के विकास के लिए कैसे हम काम लगाएं, इस बारे में सोचना पड़ेगा। ऐसा नहीं है कि ये ऑनलाइन किया गया है तो कहीं कभार ये भी होता है। हम सब इसके जानने पहचानने वाले भी है कि हमारा आउटपुट माइक है वो तो बंद रखना ही पड़ता है। हम अपना वीडियो भी बंद करते हैं और कहीं ना कहीं दूसरे काम में लग जाते हैं। दोस्तों अभी तो ये शुरुआत है, मगर ये जब दोनों साइंटिस्ट की बारी आएगी, उस साइंटिस्ट को सुनना है और वो जो बताएं उनको नोट डाउन भी करना है। आज की दुनिया में डिजिटल युग में ये हो गया है कि लिखने की बात छूट रही है, लिखने से ही दिमाग काम कर रहा है। ऐसा मैं नहीं कहता, विश्व के सब वैज्ञानिकों कहते हैं, विश्व के सब मनोवैज्ञानिक कहते हैं, यहां तक कि हमारे ऋषि मुनियों ने भी यही कहा था। तभी तो बरसों से हमारे यहां जो चल रही है वैज्ञानिक पद्धति, जो कि आयुर्वेदा में धन्वंतरी और चरक संहिता के नाम से चल रही है, हमको तो आज तक ये पता भी नहीं था कि अगर छोटी मोटी बीमारियां होती है तो उनकी हर तरह की दवाइयां हमारे रसोई घर में रहती थी। जैसे जैसे ये मेरा कहा ना कि देश के यशस्वी प्रधानमंत्री नरेंद्र मोदी जी बोलते हैं कि मेरा देश बदल रहा है, मतलब हर तरह से बदल रहा है। और हमें उन्होंने जो दिखाया है रास्ता, उन्होंने बहुत अच्छी एक बात भी कही कि सपने बड़े होने चाहिए और वो सपने साकार करने का हमें सामर्थ्य भी होना चाहिए। आओ सब मिलके सामर्थ्यवान बने, आओ सब मिलके अपने देश को विकास की ओर ले जाइए, विकसित भारत बनाए। इतना ही नहीं, जैसे बताया गया है हमारे देश की इकोनॉमी भी $5 ट्रिलियन बनानी है, उनमें भी हम सब लोगों का योगदान है। ऐसा नहीं है कि हम बाहर से साइंटिस्ट है, वैज्ञानिक है, हमारा क्या। अगर आज देखा जाए तो चंद्र के ऊपर गगनयान भी जो साउथ पोल में लगाया तो दुनिया का पहला देश मेरा देश भारत बना। इस भारत की भूमि और इस भारत के वैज्ञानिकों पर हमें बहुत बहुत गर्व है। ये ज्यादा न कहते हुए, ये जो विज्ञान यात्रा सौराष्ट्र विश्वविद्यालय के भौतिक शास्त्र भवन के अध्यक्ष और हमारे अजीज डॉक्टर निकेश शाह ने एक ठान ली थी कि कैसे भी हो ये विज्ञान यात्रा गुजरात में या सौराष्ट्र में हमारे यहां से शुरू होनी चाहिए। और इस विज्ञान यात्रा विकसित भारत की ओर ले जाने की जो ठानी है, आइए हम सब साथ मिलके उनका सहयोग करें और ये विज्ञान यात्रा का भी सहयोग करें। साथ ही में जिन जिन लोगों ने इनमें योगदान दिया है, जैसे गुजकोस्ट है, हमारे दोस्त नरोत्तम साहू जी है, डिपार्टमेंट ऑफ साइंस एंड टेक्नोलॉजी DST है, और नहीं जाने IUSC है, कितने कितने जिन लोगों ने यहाँ योगदान दिया है, उन सबको भी सौराष्ट्र विश्वविद्यालय के विज्ञान विद्या शाखा के अध्यक्ष के तौर पर सबको बहुत बहुत बधाई, धन्यवाद। भारत माता की जय, वंदे मातरम, जय जवान, जय किसान, जय विज्ञान, जय जय वंदे मातरम।
शुक्रिया अभिमानी सर, आपके इन महत्वपूर्ण शब्दों के हम अत्यंत आभारी हैं। Moving ahead, now I please request Professor H.O. Chetwa sir, Professor at Department of Physics, Saurashtra University, Rajkot, to kindly chair the session.
Afternoon, all of you. I heartily welcome all the dignitaries and the participants. I have an honor today to welcome our today's sir. He is a well-known personality in the field of science and research. He has obtained his master as well as doctorate degree from Saurashtra University. At present, working as a scientist at UGC Consortium for Scientific Research, Mumbai Center. He has completed more than 21 collaborative research projects. At present, 11 CRS projects are in progress. Total work experience of about 17 years as scientist at UGC DIE CSR. He has worked as a project fellow in a research project funded by UGC DIE CSR Mumbai during his PhD work. He has published
He has more than 324 publications and conference presentations. Overall citation is more than 3,000. Overall H index is more than 30, as well as more than 100 IPN index. He has expertise in the crystallographic and magnetic structure determination using X-ray and neutron powder diffraction method. Expertise in the magnetic, electrical, and thermal property studies of novel magnetic materials for identifying the application potential. He has expertise in the synthesis of materials, oxide, and intermetallics in polycrystalline and nanocrystalline forms. He has received many awards, fellowships, and recognitions from various institutes. So it is a very great moment for us to have Professor Rayaprol today as a resource person. So I invite him to deliver his lecture. Rayaprol, sir.
Thank you very much, Dr. Jetwa. And it is indeed my pleasure and honor to be part of. Can you hear me? Yeah. Yeah.
Yes, sir. Yes, sir. Yes.
Yes. Okay. Yeah. Thank you. So at the outset, I would like to thank Dr. Jetwa for nice introduction, and Dr. Nikesh Shah and David for inviting me to be part of this Vigyan Yatra. And being an alumni of the department and the University of Saurashtra University, it is indeed my privilege and pleasure for me to be part of this yatra. And I thank you all the organizers of physics department and the other agencies for this. So before I start, let me share my slides with you. Okay. Okay. Yeah. I'm sorry for the delay. Yeah. So yeah, the topic which I have chosen for today's presentation is neutron diffraction and the importance of neutron diffraction in material characterization. Since David had told me to talk about material characterization and material science, I think if you just look upon our whatever materials we use in our daily lives, so everything from cosmetics, the time we get up to time we go to bed, we are using materials in many forms like cosmetics, it can be textiles, it can be pharmaceuticals, transport, okay, with different types of metals and fuels which we have been using. And most important part of our lives nowadays is the computer phones and accessories. And most of them which we are using in recent times are based on technologies like on hard disks, on materials and all that. So the kind of work which we do is mainly related to some of these technologies and some of the materials which goes into these technologies. Okay, so based on that, the plan of my presentation is that before I go to the scientific part, I want to give you some brief idea of what UGC CSR is, what is my organization, what we do, and how can we help you, particularly people working in the field of material science and condensed matter physics. How can we help you in getting the best results, which which will help you to compete with the world type of diffraction, the type of equipments which we have in our consortium. Then we'll go to the scientific part. We go to neutron diffraction. We have some neutron beamline in India. I would just like to highlight you on one of the beamlines which we have been working. And using some examples from my own studies, I would like to emphasize and to bring to your notice how powder diffraction or neutron powder diffraction is useful in characterization of materials, and how it helps in explaining certain things which usually is lacking from other techniques. So it helps you to complement the physical property studies and to get a better idea of what is going on with your samples. Okay. So to begin with, the Inter-University Consortium for DAE facilities was, as it was envisaged, was started by UGC and DAE through a memorandum of understanding. The basic idea was for creating IUCs was felt by one committee headed by Professor Yashpal, and they found that in university systems, it is very difficult to have high-end equipments. Okay, and there were many national facilities set up by DAE, like the reactors and synchrotrons, which had to be utilized by universities so that it adds value to their research. It has better utilization as a facility, and it will create a pool of researchers and talent which can utilize and take benefit of this and enrich the material science community. So with this, in 1989, the UGC was set up with 3 centers at Kolkata, Indore, and Mumbai. And in around 2003, new Kalpakam node, 2011 new Kalpakam node was started. And in 2003, IUCDAF was renamed by as UGCDA CSR, the present name, with an enhanced mandate of including engineering sciences and radiation biology also as part of the program. So this is the website of our website with the photo of our head office at Indore, and what we do and why and how we do that. Okay, so how can we benefit and why? The why is simple, that our mandate which is given to us is to provide access to big science facilities of DAE and the state of art facilities which we have created in our centers at Indore, Mumbai, Kolkata, and Kalpakkam, and to the researchers in the university system. It is not only the extension of the facilities, it is also the extension of the expertise. We help you with the data, not only with data collection, but data analysis and till publications. So right from conceptualization of a problem till the execution as a publication, we will be of help to you. Okay. So what we do is that in Indore you have RRCAT, in BRC you have Dhruva reactors and other facilities of BRC which are now accessible. In VSS in Kolkata you have variable energy cyclotron, you have this INGA collaboration, you have gamma irradiation facility. In Kalpakkam there is a 200 kV accelerator which is available for material science. What we do is that we do value addition, like this high-end facilities like beam lines at Indus. You have soft X-ray beam lines. You have different types of beam lines with RRCAT, which are now accessible through us. You can study most of them. Do material preparation like bulk samples, single crystal thin films, nanomaterials. You can do a lot of material characterization. We have some theoretical support now at Indore, so you can actually discuss your problems for theoretical calculations with our colleagues, and they can add value to your research also. Similarly, in Bombay, we work on a powder diffractometer, where again, in addition to that, we have some facilities which I will just shortly touch upon, which can be used. We work basically on magnetic materials, so magnetism is a big core of our research. And we also have a colleague who used to work on condensed matter physics and ferroelectric materials. And of course, in addition to the powder diffractometer which you see here, you can access any of the diffractometers which, or any of the neutron instruments which are present in this reactor hall, as well as in BIRC. At Calcutta, we have this INGA facility and gamma irradiation facility, and of course, we have a lot of in-house facilities for structural studies, spectroscopies, physical properties, and so on. Now we have a lot of focus been given to radiation biology at Calcutta Center. So those who are interested in this can approach our colleagues at Calcutta, and they can guide you on what type of materials and what kind of work they do and how can it be beneficial to you. Okay. Similarly, at Kalpakkam, we have material preparation facilities. We have some basic characterization facilities. We have computational facilities for carrying out material studios, calculations or DFT calculations using material studios. And we also have a 200 kV accelerator accessible to us at Kalpakkam. Right. And how can you utilize these facilities is through what is known as collaborative research schemes. This can be one-time experiments like short-term. You just want to do say X-ray or you want to do neutron for one sample. You can just write to us. You can come bring your sample. You can do the analysis. You can do the you can collect the data. You can do the analysis. We can help you with that. Or you can have a long-term commitment with a typical project which runs to 3 years. As previously as was introduced, like I was an IUC student, so I was one of student in one of these IUC projects with Dr. Kuberkar at Saurashtra University, and it is during these projects that I started learning neutron diffraction and analysis of diffraction data, and which is now helpful for me because I am part of this program in IUC now. So like that, you can the students can come and learn, and the faculties can write this long-term proposals for 3 years, and you can get. It's not a major funding project, but what it shows you is a beam time as well as access to all the facilities of the centers. So what we do in-house facilities at Bombay is that the mandate for us is to utilize these in-house facilities and several neutron scattering facilities at Dhruva and others operated by SSPD and make them accessible to university utilization through long-term and short-term projects. And we also coordinate utilization of these facilities for university researchers, our in-house as well as BRC in-house facilities. So this is a brochure which we had just brought out, which gives you an idea about what type of broad research areas we do at Bombay Center, what type of studies are possible for materials. You can do structure, dynamics, films, multi-layers, and you can do activation analysis, neutron imaging, and a lot of facilities which are available within BRC as well as within SSPD and UGC, and as well as other facilities like you can have LEHIPA linear accelerator facilities, electron beam accelerators. You can have a spectroscopy, XRF small angle X-ray spectroscopy, and so many things which are available at BRC can also be accessed through us. Coming to our beamline, we have set up. I mean, UGCDA CSR has set up a focusing crystal diffractometer, which is now called PD3 at Dhruva, which has a unique sample environment and which is with a magnet as well as a cryostat. That means that you can do neutron diffraction experiments at different wavelengths depending on the material which you are studying. You can do it as a function of temperature or as a function of magnetic field. And we have an array of 12 linear helium-3 detectors, which gives us a very good throughput. So we have very good signal to noise ratio, as you can see, and we have very good resolution to very high angles also. So that helps you to understand the structure to very precisely, as far as high angles are concerned. That means very small d spaces you can easily resolve and get the proper cation distribution, bond angles, bond lengths, and so on. So whatever information you can gather from neutrons, you can get that information on this diffractometer with very good resolution. This is one of the best diffractometers in the country right now, and it is on par with some of the best in the world also. Of course, ours is a moderate flux reactor, so the flux is an issue for us. But otherwise, as far as resolution is concerned, this is also one of the best. So these are our colleagues who are working at Bombay Center, and these are the research interests or specializations of this. And if you're interested to collaborate with them, you are free to write to any of them. Okay. In addition to neutron diffraction, we have what is known as a physical property measurement systems. We have one relic fire based as well as a cryo-free system with a magnetic field up to 14 Tesla. And there are a lot of measurements which are possible. You can do DC magnetization like with a VSM. We have AC susceptometer. You can do AC susceptibility measurements. Of course, the temperature range and field range remains the same for all the measurements. We can do DC resistivity, electric transport like ETO, Hall voltage measurements and all. We have a horizontal sample rotator also. So that means if you want to do measurements as a in plane and out of plane measurements with field parallel and perpendicular to the sample surface, so all those measurements are all possible with these facilities. We can do thermal transport measurements like heat capacity and thermal transport, means You can measure thermal conductivity, Seebeck coefficient, and thermoelectric figure of merit. You can calculate from all these measurements. Now we are going to procure a broadband FMR also. That will give you a very good idea about the that is mainly useful for thin films, but it will give you an idea about the magnetization of thin films and things like that. We also have a very large broadband dielectric spectrometer, which can be used from low temperature, from liquid nitrogen temperature to room temperature, and with the additional accessory of a high temperature furnace, we can go up to 1200 degrees centigrade. The frequency range which we can measure is from 3 microhertz to 3 gigahertz with a network analyzer, and this is that network analyzer, and this is all automatic systems. So in addition, we have some sample preparation facilities using for oxides as well as for intermetallics. And we have just bought a spin coater for thin films. And of course, we have an X-ray diffractometer for doing basic X-ray diffractions. To utilize our facilities either at Bombay Center or any other center, you can use the CSR portal. You can write your proposal, one-time proposal or long-time proposal, and you can follow these steps at the portal and submit your proposal. Some of us will definitely revert back to you with the details of how to carry out these measurements. Okay, so with this, we'll now come to the scientific part of this present talk. So the topic is neutron diffraction, how important it is in material characterization. And when we talk about materials, when we talk about magnetic materials, because that is what we have been doing. So this is just for comparison. I think this is something which you had already seen. This is, if you can identify, this is a IBM hard disk of 1956, and this is something which is available in the market already now, 22 terabyte of hard disk. And what is predicted was to available by 2023 was 26 terabyte of hard disk, which is now available for data centers. But if you just want to compare what happened in 1956 and what is presently available in the market now, is that the storage capacity of this bulkier machine, this is like 1 ton at that time, was about 5 megabyte. And the cost was about $35,000 of that time. And now we have a 15 terabyte of hard disk, which weighs something like 300 grams, and the cost is about $500. So you can see the vast change. Okay, from a huge 5 megabyte, we have an email which can be more than 5 megabyte in size, right? So what has changed between 1956 and 2020? That is mainly the material which goes into making this hard disks. Okay, so initially it was most like a wire bond and electronics circuits. Now, because of the advancement in magnetic memory storage technologies, you can have a tape which can, if it is wound around, it can give you a 330 terabyte of data in one storage device. So the leap in data storage is more than 6 lakh percentage times, roughly in 60 years. Okay, and you can see the change in the affordability. It was highly unaffordable. Now it has become highly affordable. Another example which we can easily relate to is the change in the way we communicate. Okay, so this was like, if you talk about the mobile cellular technology, we had 1G about in 1981, and in about 40 years time we have gone from 1G to about 5G, and we are going to 6G very soon. Okay, so 5G was started sometimes last year in commercial rollout, and the testing of 6G, the technology being developed is already there, and it is expected by 2028 we can hope to see commercial launch of this 6G technologies. So what has changed in these years is the materials, along with, of course, technology and development in other areas. It is the material which goes into making these electronic devices. So material science plays a very crucial role in the development of any science and technology, right? So if you look into the sciences, what we have studied in school and colleges is that we have physics stream, chemistry, biology, and engineering. But material science and engineering is a stream which is actually not the segregation of the different science subjects, but it's an integration of different aspects of or different disciplines of sciences, which comes together to give you material science. Okay, so this was probably the first example of a new academic discipline emerging from fusion rather than fission. Nowadays, as you see in many of the government documents, you would have seen there is a lot of emphasis on interdisciplinary research. And I think material science is one area of research which actually encompasses multiple, which actually follows that to the T. So what do we do? If you just Google or go to Wikipedia and look for material science, you will see a huge page with a lot of things which can be done. Of course, one person cannot do everything. So we choose something which is possible for us to do or something which is of our interest. So if you look into what we do and what we focus on is the synthesis, structural and physical property characterization. And our main focus has always been in trying to correlate the physical properties with the structural characterization, with the structural properties. And it is in this domain that neutron diffraction, which can be useful for both crystallographic structure or nuclear structure as well as magnetic structure, comes into picture. Okay, and this is the area which I'm going to give you some flair of how neutron diffraction can help in understanding the physical properties. So that is what I was saying, that we're trying to correlate the magnetism and multiferrocity using neutrons. Okay, so why structural property correlations are important to study? If you look at the allotropes of carbon, okay, you see that there are crystalline allotropes and amorphous allotropes, and there are different examples like diamond, graphite of crystalline allotropes. There are amorphous ones like coal, charcoal, lampblack, and so on. If you focus on crystalline allotropes, you have diamond and graphite, for example. These are well-known examples, but we know that though they are allotropes of carbon, they are made up of same type of carbons, but the way they behave, they're totally different. Diamond, as we know, is the hardest substance with very high relative density. It has a very high refractive index. It is a non-conductor of heat, which burns at around very high temperatures of 900 degrees. And it occurs in octahedral crystals. So it has a very good shine and all. So graphite is soft and easy, black and opaque. It is a good conductor of heat and electricity. It burns before diamond at something like 700, 800 degrees. It usually occurs in hexagonal crystals. So it is a layered structure. So it is easy to peel off layers of graphite because of the way it is bonded. Okay, it has a flat parallel layers and of regular hexagons. So you can actually peel them off layer by layer. But the way the carbons are bonded in a diamond, you see that it forms a three-dimensional network of covalent bonds, and which makes them very hard and brittle. So how can we say that this is like this and this is like this? Is on the basis of the structure which we have studied. And from those structural properties, we can understand how the physical properties of diamond and graphite are and why they are different. So the knowledge of crystal structure helps in understanding the physical properties. And if we are working on magnetic materials, then you can determine the magnetic structure, and then you can help you to understand how the magnetic structure helps in understanding the magnetic properties as well as. So if you have materials, and if you are looking at particular characteristics of materials, then if you understand the structure dynamics or structure property relations, you can actually prepare your materials or tailor your materials as per the characterizations which you are looking forward to. So to do the structural analysis, you need different probes. Okay, so you need different kind of probes which are available are either electron, you can do electron diffraction, X-ray diffraction, or neutrons. In case of electron diffraction, you are looking at a very point source because of this electron-electron interaction of electrostatic type, electrostatic interactions. You can scan the surface in thin sections and very close to the sample surface. It is useful for studying the short range ordering. We are looking at very small area of few nanometers or micrometers, and you can understand how the dynamics is, how the structure or layering is, morphology is in that small region. But there are some disadvantages of using electron diffraction, which I think you all must be knowing. Next is the most visible and most widely used technique is X-ray diffraction. X-rays, as you know, are electromagnetic radiation, so it has this electromagnetic interaction of incoming photons with the electron cloud in your sample, and it can give rise to a lot of structures, in structural information like cell parameters, bonding and all that. It is useful for phase identification and determining unit cell parameters. Of course, the problem with the X-ray diffraction is that it depends upon the number of electrons present in your sample. So it is strongly Z dependent, because the electron clouds, the more the number of electrons you have, the more stronger electron cloud you have, the more scattering will be, right? Which is not the case with neutrons. Neutrons being chargeless, so it can penetrate deep into the sample, and it can actually interact, the neutron can interact with the nucleus in your sample, of the atoms present in your sample, and because of this nuclear interaction can get scattered, right? So the advantage is that it is not Z dependent, like unlike X-rays. So therefore you can identify lighter elements in the presence of heavier ones. You can do phase quantification, you can determine the cation distribution, oxygen stoichiometry, thermal parameters, and so on. But unfortunately, not all elements are neutron scatterers. There are some neutron absorbers also. And of course, it is expensive. It cannot be done so readily. So you have to go to neutron sources like reactor or a synchrotron or a spallation source to do the neutron diffraction experiments. But another advantage of neutrons is that it has a magnetic moment. It has a magnetic dipole. So because of this, there is an electron. It can interact. The spin of the neutrons can interact with the spin of the unpaired electron in your sample. Because of this dipole-dipole interaction, it can do the magnetic scattering, right? So in addition to structural information, you can get the magnetic structural information because of this magnetic interaction, which of course is a electron dependent one, but definitely it gives more information of the magnetic structure, which no other technique can give you. So if you look at the properties of thermal neutrons, so from reactor source you get a plenty of neutrons with different energy levels. You can have slow neutrons, you can have intermediate neutrons, fast neutrons, and so on. But what we are interested for diffraction purposes is the thermal neutrons, which has a kinetic energy of about 25 MeV at room temperature, and that is in terms of wavelength, it is comparable to the wavelength which we see for interatomic distances, about 1 angstroms or so. So to look into the properties of neutrons, it behaves like a particle. It can behave like a wave also. So it has a mass, it has a spin, it has a magnetic moment also. Since it behaves like a wave, it can have a measurable wavelength with a measurable scattering length. So this makes it very attractive for carrying out neutron diffraction, particularly for magnetic materials, because you can determine the magnetic structure also. To give an idea about how the neutrons and X-rays can behave, if you look at the X-ray form factor and the neutron coherence scattering length, you can see that copper and zinc, if you look at the periodic table, they are 1 electron apart. But if you look at the X-ray scattering, they are almost identical. Whereas in case of neutrons, you can easily distinguish between copper and zinc. So if you're having a compound with copper and zinc, it will be difficult to identify how much is copper and zinc with X-rays. But if you do neutrons, that will be more prominently seen. Another important part in terms of neutron is the scattering cross-section versus absorption cross-section. In case of, for a good scattering from neutrons, your scattering cross-section should be higher than the absorption cross-section. If you look at the example of lead and oxygen, you can see that in case of lead and oxygen, the lead is the one which is dominant over the oxygen in case of X-ray form factors. Whereas in the case of lead neutrons, the coherent scattering can give you easily distinguish between lead and oxygen. You can determine their presence. And in terms of absorption scattering cross-section, you can see that the scattering cross-section for lead and oxygen is much higher than their absorption cross-section. Okay, in the same example, you can see that in case of gadolinium and boron, the absorption cross-section is much higher than the scattering cross-section. So if you have your gadolinium or boron or vanadium in your sample, it is very difficult to get the scattering from these elements, because these can absorb neutrons more than it can scatter. Okay. So to do neutron experiments, you have to go to source where neutrons are available. What you see in what you see in yellow here are all reactor based sources. Basically, they depend upon the nuclear fission reactions to generate neutrons. But the other ones which you see in red are called spallation sources, which are much more safer these days compared to nuclear reactors, because in spallation sources you are not using a fission reaction, but you are bombarding a very heavy energetic particle on a very heavy metal and knock off the neutron from there, right? So it is more safer in terms of radiation these days, and that is more preferred also. But in India right now we have only reactor sources, and that too is available in BRC also. So in BRC there are two reactors, Cyrus and Dhruva, which were responsible for carrying out neutron scattering experiments. These are all research reactors. Cyrus has been decommissioned now, so only reactor available right now is Dhruva, where all the action is at the moment. There is a plan of proposal of constructing a new reactor with a better flux and better facilities at Vizag, which will be available, I think, in another 5 to 10 years now. At Dhruva, this is the reactor hall, and there are plenty of neutron scattering experiments which are available. You have a single crystal diffractometer, you have a triple axis spectrometer for carrying out inelastic scattering, you have polarized analysis spectrometer. You can do polarized measurements, means you can polarize a neutron beam and you can carry out the diffraction experiments, scattering experiments. You have 3 powder diffractometers. There is a new inelastic spectrometer coming up here in the place of filter detectometer. There is a new beamline for imaging which has already come up, which is not there present in this image. Then you have a high Q diffractometer where you can actually measure diffraction patterns up to very high angles. Similarly, you can do small Q experiments also on these two instruments called small angle neutron scattering experiments. You have polarized neutron reflectometer where you can study thin films, and like that there are other instruments which are present in the Dhruva reactor hall. So this is some specific specs of our diffractometer. I work on PD3 at a neutron diffractometer. So here is a tandem beamline, because since there are not space available here, so we had to bring the neutron out. And there is a monochromator here somewhere in present. And we use an open beam geometry. So whatever the neutrons comes from the reactor, we focus it on to the single crystal monochromator, which is our perfectly bent single doubly focusing monochromator. It bends the neutrons and pushes them onto the sample. This is from the point where it comes out of the reactor, falls on the sample. This is a cryogen-free magnet. It is a 7 Tesla magnet. It has an opening window somewhere here, and there is an outgoing window. So what we do is that neutrons falls on the sample, is scattered in the plane, and it is taken up by the detectors which are housed in this green assembly. So we can do have neutron diffraction in different sample environments. We can do as function of temperature. This is a closed cycle refrigerator which is helpful to do neutron scattering at a very fast rate. Okay, so we can reach the lowest temperature in about 2.5 hours. This is a magnet which has a very huge volume, so it takes about 27 hours to reach the base temperature. And then we can do neutron diffraction. We can change sample at any temperature, which is similar to both. And then we can do neutron diffraction. For doing collecting one typical set of diffraction data, means you collect one pattern for diffraction data. Say for one sample, it takes about 2 to 3 hours to get good data, which is refinable. Okay, so if you want to do it as a function of temperature and field, the time adds up like that. Okay, so if you want to 10 temperatures, it will take something like 20-24 hours for one sample. So it is like that. Okay, now coming to the physics part of this. So now we are using neutrons and we want to see how we can connect magnetism and ferroelectricity. So let us touch upon this aspect using 2 examples. So my main interest is working on low dimensional spin chain compounds, which, as we know, has very large interest in spintronics these days. So I will touch upon that part and how neutrons are useful in the process. So for magnetism, we know that we have different types of magnetism. We have ferromagnets, antiferromagnets, ferrimagnets, and paramagnets. And based on our experiments, like from susceptibility or magnetization, we can identify which is what, right? You have a TC in a ferromagnet, so you can know how the TC is, why there is a transition between paramagnetic to a ferromagnetic state, and at what temperature that transition takes place. We know from susceptibility what is an antiferromagnet is, how the ferrimagnet will look like, and how the paramagnet should behave, and so on. But if you look at the structure, if you look at the dimensions, you have a ferromagnet. So by definition, we say that all the spins are aligned in one direction and the magnitude of all the spins are same. In case of antiferromagnets, the magnitude of spins are same, but the spins are aligned opposite to each other, right? So if you want to draw a magnetic cell, you have to go to the spin up portions. You can see that it has to travel a lot compared to the ferromagnet. However, in case of a ferrimagnet, you have a superstructure reflection, which means you have spins which are anti-parallel, but the spin moments are not of same magnitude. So you can consider ferrimagnet as a special case of an antiferromagnet. But the difference lies in the unit cell dimensions, and I will come to that. So if you talk about geometrical arrangement of atoms, so if you have all those, okay, this should have been interacting. It should have been upwards. So we have spins which are all in one direction, that is ferromagnetically aligned. But in case you have spins which are oppositely aligned, so on a triangular lattice, the third spin becomes incoherent because it doesn't know whether it should align parallelly or anti-parallelly. Okay, so the third one remains incoherent. That gives rise to what is known as topologically induced geometrical frustration. Okay. So in most of these low dimensional systems, where we have mainly because of this type of triangular lattices or topological reasons, you can end up with having frustrated ground state or magnetic ground states, which are not yet completely zero, but they don't exhibit long range magnetic order also. Okay, so there's a lot of interest in studying low dimensional systems, because in electronic devices which exhibit very interesting electronic and magnetic properties, because if you look at microchips which has a dimension of less than 100 nanometer, the electronic components can go to this low dimensional regimes. So you don't see long range magnetic order, but there is a small magnetic component which has a net zero component. Okay, so there are so many examples of this low dimensional systems which show interesting electrical properties like metal insulator transitions. You can have charge density waves, superconductivity, Halden spin gap systems, spin parallel transitions, partially disordered antiferromagnetic structures, and so on. So we'll touch upon Halden gap in the next example. But talking about this quasi one-dimensional compound, we have a situation in this where we have two magnetic transition metal ions. It can be magnetic, it can be non-magnetic also, but one of them has to be magnetic. And when you place them alternatively along the c-axis, there is one phase. So when you have octahedral and tetrahedral positions which are alternatively shared, you have magnetic and non-magnetic ions which are alternatively placed. So you have this oxygen which is shared between both these transition metal ions. Okay, so which forms the common surface. But you can see the interaction is mainly along this particular chain, so that is why it is called quasi one-dimensional. And if you look at this A3MXO6 type of structure, there are different type of compounds which are available. Stoichiometrically, they look identical, but if you look at the structures, they have a different structures. The moment you put copper at the tetrahedral positions, you see that because the copper being a Yantilar ion, it can move out of its square prism coordination, and it reduces the symmetry of the system from rhombohedral, which is more with a hexagonal unit cell, to a monoclinic structure. So the monoclinic, as you know, has a low symmetry compared to hexagonal. But there's one exception to that. If you have calcium, copper, manganese, it is still lower than in terms of monoclinic. It has the lowest symmetry. It's mainly again copper-based system which has this kind of properties. So you have composition, you have structures, and you have variety of magnetic properties which are available within this stoichiometric compositions. Now, if we take an example of okay, here again you can see the structure is drawn like this. This is along the AB plane, and this is the structure which you see from the top. If you see that you have this different chains which are placed along which are placed along the this is the top view we are seeing. They have different unit cells, so you have different chains at the edges, and you have chains in between also. If you see carefully, this forms a rhombohedral unit cell actually, but if you take all these chains together, this forms a hexagonal lattice. And when you have a hexagonal lattice, you can have a triangular arrangement of the lattices also. Okay, so when you have this kind of arrangement, you have two chains with and a third chain with a different cation at different positions, you can have different kind of geometrically frustrated ground states. Now in this example, if all the chains have coupled ferromagnetically, then the intrachain coupling is also ferromagnetic. So the end result will be a ferromagnetic ground state. But if you have an antiferromagnetic arrangement of this different chains, then the third chain or the chain at the center of this hexagon will remain inconsequential. It doesn't know whether to order ferromagnetically or antiferromagnetically. So that gives rise to magnetic frustration. So because of this frustration, you can have very interesting physical properties or magnetic properties also. So if you look at multiferricity, now coming back to multiferricity, that is the second topic we were discussing. So it was the Pierre Curie who said in about 1959 that two phenomena like piezo-magnetism, that means you can have a linear coupling between magnetic field and this deformation within a solid, and this linear coupling between magnetic and electric field can also exist. So you have the coupling between magnetic field and a piezo-magnetism or the deformation, or that is ferroelasticity, or you have a coupling between the magnetic order and the ferroelectric field. So these two phenomena, he said, could exist in theory, but at that which could be seen in magnetocrystalline symmetry of that time. But in around 1956-59, when Curie made these predictions, he said that it has been not observed in any substances. But later, sometimes in I think 1959 only, Zelensky predicted that this can be observed in Cr2O3, that you can exhibit linear magnetoelectric effect. Okay, but where he said that the electric and the magnetic part can be intimately connected with the magnetic symmetry of the substance. That means if you look at the magnetic structure, then the magnetic symmetry may allow the coupling between the magnetic and electric part of the magnetic and electric phases in Cr2O3. And this was experimentally shown that in Cr2O3, Astro showed that there can be a coexistence of ferromagnetic and ferroelectric coupling. But the problem is that you can have ferroelectric part, you can have ferromagnetic part in one sample, in one phase, but whether there will be a coupling between these two. And this was the basis of what is known as a multiferroic systems. You see several examples of ferroelasticity, ferromagnetism, ferroelectricity, and ferrotoroidicity. But the most important one which being studied from application potential is ferromagnetism and ferroelectricity. And the coupling between these two is what we call as multiferroics. But it's not only the coupling, it is a cross coupling between these two ferroelectric orders which makes them suitable for spintronic applications or any other applications which we are talking about. What you mean by that is that if you have a ferroelectric phase, you have a magnetic phase, then by applying electric potential, you can change the magnetism, or by applying magnetic field, if you can change the polarization, that will be the cross coupling which should exist in the same phase. So if you go by this combination, you can have four types of logic states. You can have ferroelectrics, you have ferromagnets, and then you can cross couple between them, and you can have change the magnetic field, change the polarization. You can change the electric field, and you can influence the magnetization. So this is what makes the multiferroics very interesting us. Now, if you go deeper into this, they have two types of multiferroics. You have type 1 multiferroics, which are older, which were originally observed, where the ferroelectricity arises due to structural distortion, which occurs at high temperature, and the magnetic order usually antiferromagnet sets in at low temperature. Okay, so in this type of multiferroics, you have both the ferroelectric orders present, but they are independent of each other. Okay, but in type 2 multiferroics, magnetic order breaks the inversion symmetry, and because of that, you can have uh, the ferroelectric and magnetic transition taking place at the same place, and it is the magnetic transition which causes the ferroelectricity in this type of multiferroics. The one example of this is TBMNO3, where it can have two transitions like 41 and 28 Kelvin, but it is at 28 Kelvin that the magnetic structure changes, that is, the magnetic symmetry breaks, and there is a onset of the electric polarization. Okay. Now, if you look at the classification of multiferric materials, you have type 1 multiferrics like bismuth ferrite, where because of the shifting of this lone pair bismuth ions towards these oxygens, that causes the displacement of the polyhedra, and then that can give rise to spontaneous polarization in the system. You can have geometric frustration also, as we have seen. In this case also, that the movement of this polyhedra or bipyramids can give rise to displacement, which can yield the polarization. You can have charge ordering also. Because of this charge ordering, because of the charge ordering, there is a movement of these planes, and because of the movement of planes, you can have the polarization. In type 2 multiferroics, you can have what is known as inverse DM interaction. Because of this DM interaction, you can have interaction between alternating spins, which can actually give rise to displacement of the ion. Basically, in case of this DM interaction, you are talking about the canting of the spins, or you're looking at the spinal structures, spiral structures in magnetic structures. You can have exchange friction also, like in up down down in configuration, which we see in CSEO MnO6. Because of this kind of movement of spins towards each other or opposite to each other, can give rise to this polarization. You can have spin dependent hybridization of p and d orbitals, like in MXO4 tetrahedra, or like in copper iron ferrite, the copper iron oxide. Because of this orbital hybridization, you can see the movement of these crystallographic terms, which can give rise to net polarization. And why do we study? As I said, they have a lot of interesting applications in different devices. If you have an electric field control of magnetism, you can have spin electronic devices, tunneling magnet resistance, and so on. You can use it for high frequency radio devices like filters, oscillators, phase shifters. It can have applications cosmology, particle physics, photovoltaic effect, photocatalysis, gas sensing, and so on. Now coming to some examples, like again going back to CA3CO6, we have seen that it has a geometrical structure. It has this kind of a frustrated ground state. It can have frustrated ground state in the event that there is an antiferrometric ordering among the chains. So if you look at the magnetic susceptibility, this shows that it has an antiferrometric order, which at Neal temperature of over 15 Kelvin. If you look at the ratio of theta p to Tn, it indicates that there is some kind of frustration already present in the system. Because if you calculate the frustration parameter, it comes out to be around 3. But if you look at the valence states, it will come to calcium 2 plus and manganese 4 plus, which makes both of them magnetically ordered. But the interaction is antiferromagnetic, and it is confirmed by this presence of this hump in heat capacity also. It's not a clear lambda anomaly, but you have a hump, which shows that spin, it may not be completely spin glass, but it has a short range magnetic order, which coupled to the long range magnetic order also. Okay. So if you look at the magnetization, again you have the spin reorientation thing. So that shows that it has a field induced effect also. And if you look at the AC susceptibility, which rules out spin glassness, but it shows there's a magnetic ordering which persists below 13 Kelvin, which is in sync with our Neal temperatures. Okay. So now there were several papers which talk about the spin up down type of order presence, which will give rise to this kind of ferroelectricity in this kind of systems. Okay. Which tells that the system can be ferroelectric. But what happens when we apply magnetic field? So we are looking at magnetodielectric effect. So when we do apply large magnetic field, we find that around 7 Kelvin or 8 Kelvin, we see there is a large change, something about 8% change at 8 Kelvin under presence of 5 field. So what happens is something which was interesting for us. So we wanted to see it through neutron diffraction. So we did carry out neutron diffraction with as a function of temperature, and we find that there is a magnetic order present. It's a long range magnetic order again. So we are able to determine the magnetic structure of that. Now, along with the neutron diffraction in zero field, we can do neutron diffraction with field also. And we find that this intensity of this magnetic black peaks changes when you apply magnetic field. But if you look at the magnetic structure and you look at the magnetic moments which you get from the magnetic structure, it shows that when you are in zero field at 10 Kelvin, we have this antiferromagnetic structure between cobalt and manganese. Cobalt is ferromagnetic and manganese is antiferromagnetic, but cobalt manganese interaction is antiferromagnetic. But the moment you apply a phi Tesla field, you're turning all the cobalt into positive side, you're making them align along the C axis, and you have a net ferromagnetic moment. So you have field induced changes, which we saw in magnetization also. We saw that in the magnetodielectric effect also. So this shows that when you apply magnetic field, there is a change of cobalt moments from antiferro to ferromagnetic order. Okay, so next example I will take very fast is this TB to BNOFI. Our interest was same because this is a Halden spin chain system. So you have different sets of gap if your spin integers are where spins are integers of half integers. Okay, so what Halden predicted was that there is an excitation gap if your spins are integer spins, but if you go away from spin to half from integer to half integer, the gap closes. Okay, so this was a theoretical prediction which was later confirmed by experiments on YB2BNFI, which has a spin 1 ground state, spin 1, which exhibits this gap in the excitation. But the moment you dope a rare earth ion which has a magnetic moment, it goes from spin half towards spin half, and you lose the excitation gap in that. So that was the main motivation of studying this one. But then this is a group of Professor Sampath Kumar, which they did a lot of interesting work on the multiferric properties of these systems. And among them, they find that TB2B NOFI was one, which exhibited large magnetodielectric effect. So what it shows is that in heat capacity or magnetization, you find that there's a small humps at 62 and 25 Kelvin, which are confirmed to show a change in magnetic order. Okay, from T1 to T2, it is an antiferromagnetic order, and T2 is another antiferromagnetic order. So there's an order to order transition. But if you look at heat capacity, you don't see any anomaly around 62K. You see only the anomaly at or field dependence anomaly at 25 Kelvin order. So if you look at the dielectric data as a function of field, also you will find that at 25K only you see these anomalies. But if you look at field induced magnetization or magnetodielectric effect, you see that there is a hysteresis available, which shows this metamagnetic kind of transition at intermediate fields, and it has a field dependence also. And this is the temperature at which we saw the pyroelectric current, and if you integrate that, you find that there is a polarization which is seen only below this 25 Kelvin. Right. So what could be the origin for that? If you look at the paper, this was the transition which was observed only at 25K, not at 63K. Okay, and it was the highest among all the rare earth based systems which was studied. So if you look at try to understand the origin, if you look at the structure, this is a IMMM space group, which if you look at carefully is a centrosymmetric space group, which means there is an inversion symmetry present in the system. So from crystal structure point of view, this is not supposed to show ferroelectric transition, but yet we see that. Second thing is that if we wanted to see if there is a temperature dependent change in this crystal symmetry, which was not the case. And when we do magnetic structure determination, we find that the magnetic order sets in at 60 Kelvin. That is where the first ordering temperature was observed. Okay, so below that temperature, you see this magnetic black peaks which evolve. But if you try to analyze the magnetic structure, we find that the magnetic space group is CM bar, which is actually a polar space group, which actually allows the ferroelectricity can be seen in this one. But the interesting point is that this space group is present at from 60 or Kelvin down to 2 Kelvin, which means there is no change in magnetic symmetry also as we go down in temperature. So the information which we are keen to show you is that if you look at the canting angle between terbium and nickel as a function of temperature, we find, and we actually calculated it using different magnetic models also, and we found it from ferromagnetic, ferrimagnetic, collinear antiferromagnet and non-collinear antiferromagnet, and we find that the calculation of non-collinear antiferromagnetic cell coincides with our observed magnetic structure. And we find that for this kind of arrangement where the terbium and nickel moments are actually canted with respect to c-axis, is where we find that the ground state is lowest, and you can get the parameters similar to the experiments. And what we see is that because of this critical canting angle, and that's the difference between the canting angles of terbium and nickel, around 25 Kelvin, below this 25 Kelvin only, we see that there is a huge jump in the canting angle. And because in this region only, we find that the system shows large polarization. Okay, the polarization is about 18%. MD is about 18%. So if you try to understand this on the basis of conventional DMI models, which is present for non-collinear magnets, it fails to show that because the structure is collinear, non-collinear, but it is not a spiral one as predicted by DM interactions. Okay, if you look at non-collinear magnetism in perovskite magnets, what the need of the theory is to have the role of rare earth ion like a terbium 4F ion has to be investigated, and right now that is actually lacking in the theory right now. Okay, so that is something which we were able to bring out from our neutron diffraction results, that the magnetic structure can play a major role in explaining the physical properties of our systems. Okay, so this is the summary of this part, that a critical canting angle plays a crucial role, and which opens up the question of the role of the 4F orbitals in which actually results in a non-zero angular orbital magnetic moment, which interacts with the different 3D ions. Like it can be nickel, it can be cobalt, and because of this interaction, we are able to see that there is a canting of the spins, and the difference of this canting angle gives rise to the magnetodielectric effect or magnetoelectric effect in these compositions. So the role of 4F orbitals needs to be included in the theoretical approach, and that is what was the major conclusion of our work. So to conclude my talk, the takeaway message which I would like to convey to you is that, as we have seen, X-rays, of course, neutron diffraction, of course, is complementary to X-rays as in electrons. It tells you about the crystalline structure, nuclear structure, and gives you cation distribution, bond lengths, and bond angles. If you are studying a series of samples, neutron diffraction is very useful in that respect. It also helps you in understanding the magnetic structure, and you can understand, as we have seen from examples, that it is important to understand the magnetic structure to explain the physical properties in many cases. And neutron diffraction becomes an important tool in understanding the structure property correlations. So I'd like to acknowledge my collaborators. This was all started by Professor Sampath Kumaran, and the guys from TIFR like Karthik, Ram, and Sanjay, they all prepared the samples, and they did the characterization, the basic physical property measurements. Dr. Tulika and her student Sarita, they did the theoretical calculations, and rest of us are involved with the neutron diffraction analysis. We carry out the experiments on our beamline as well as beamlines abroad, and we have done all the calculations. And Professor Mohiti has been all involved with us in the analysis of the results and getting beam times and all that. So with this, I would like to thank you all for your time and attention. Thank you very much, and namaste.
Thank you so much, Subhendra sir. It was such a great and pleasing presentation by you. So can we
thank you,
have
sir, for your nice lecture. Now session is open for the question and answer for the discussion.
Yeah.
We have a shortage of time, so
Yeah.
you can ask the question immediately.
And it's okay if somebody has a question, they can write to us. I will be happy to answer by email also. So not an issue.
Sir, good afternoon, sir.
Yes, ma'am.
Any
Very
question?
nice talk. Sir, I would like to ask about the DMI, DM interaction.
Yeah.
Please elaborate that.
Okay, so in case of the DM interactions,
Okay,
because
you
of
can
the-
ask your question.
Yes, sir. Yeah, so in case of DM interaction, you have because of okay, I can stop presenting, sir. Okay, so in case of DM interaction, you have two spins. Okay, and there is an arrangement of there is an interaction between these two spins through intermediary bond, and because of that interaction, there is a canting involved. That means these spins have to be canted in such a way that it minimizes the ground state, and you have a spiral structure. Okay, because of this angle which is involved. So if you go across the structure, though it may be collinear, but you have to have the spiral structure. So in our case, since the spins are not spiral, okay, we have canting, but it doesn't lead to the spin interactions. It doesn't lead to the spiral structure. Okay.
Okay, so
So
how
that
is
was-
it? Okay, so sir, how is it different from the SD exchange interaction?
What? Sorry, SD.
How is it different from the SD exchange interaction?
I'm not very sure about SD interaction, but in this case, we have interaction of TB and NI, which is basically interaction of 3D and 4F electrons, which are playing the role in this case. Okay, if you change the rare earth ion, like if you go from terbium to neodymium, though everything remains the same, the magnetic structure is different. We don't see magnetic structure may also be same, but we don't see the cation, the critical canting angle which we observe in case of terbium. In that case, so the role of terbium is also very important. It's a single ion anisotropy, so that also has to also has a role to play.
Thank you, sir.
Sure.
Okay, anybody else? Any question? Okay. So if there is any no question, then on behalf of the department and organizing committee, I thank you very much, sir, for sharing your valuable time for our event, that is Vigyan Yatra. Thank you.
Pleasure, sir. Pleasure. Thank you very much, sir. Thank you. Thank you very much, sir. Thank you.
Thanks. Okay, so we are moving towards the second session of Vigyan Yatra. In this session, as an expert, Mr. Ramcharan Meena is with us. He is going to deliver his talk about the introduction to IUSC facilities and programs. Ramchandra Meena has completed his MSc Physics at IIT Delhi, then scientist training IUSC during 2013 and 14, then scientist C in the same institute during 2014 to 2020, then scientist D at present from 2020 to till date, pursuing PhD in physics from IIT Delhi, and more than 40 publications are in his credit. 3 book chapters he has published. So, on behalf of the organizing committee, I would like to invite Mr. Ramcharan Meena for his talk about the introduction to IUSC facilities and programs. Sir.
Thank you, sir, for nice introduction. Myself, Ramcharan Meena. So first, I would like to thank all the organizers to give me an opportunity to present IUC activities So what I will do, I will basically brief the IUC activities, what we will do and how this is useful for the our community. So basically, as I have seen in the registration form, there were many students from UG, PG, and in PhDs. So what I found is, instead of giving a talk on some particular material, particular topic, research topic, it will be very useful if I can give a talk on IUC facilities, since it is a center which is established by the government to help the university systems. So basically what we will do here, peoples come from different areas. We have expertise in different areas for having different peoples in working in different areas. We take the advantage of the expertise of them and proceed in our research. So how we can use the IUC facilities, how we can apply for the IUC facilities, what are the procedures and what are the conditions, how IUC supports experimentally. So everything will be covered in my talk. So first of all, is my slides are visible to everyone? Hello?
No, sir.
No, sir.
No. Okay. So I will share. Okay, entire screen. Is the slides are visible now?
Yes, sir.
Okay. So let's start our talk. So basically, as the title of the talk is Introduction to IUC Facilities. So basically, it will cover what are the facilities IUC will have, what are the programs it have, and how one can use these facilities or these programs. Basically, how one can benefit using these programs. And it is my email ID. So what you can do, you can write anytime, and I will be happy to answer the same. So, I enter IUAC. The name is Inter University Accelerator Center. So if you open the website, the first page it shows we are having accelerators for knowledge. Basically, we build the accelerator, we work with the accelerator to help the users to create the possibilities for international competitive research within the university system. So basically, we promote the university, we promote the various users coming from different university from India as well as from the abroad to work with the accelerator facilities and enhance their knowledge, enhance their in scientific career. So it was basically established in 1984 as an autonomous institution, as an autonomous institute funded by the UGC. And it was the first IUC set up by University Grant Commission. As you know, today there are many IUCs, but IUC was the first setup, first type of institute for the similar type. And our accelerator facilities are operational since 1991. The first beam which was delivered to the user on the date 8th July 1991, and we celebrate the 8th July as a Peloton Day. Earlier, IUC was known as Nuclear Science Center, as the focus on the basically majorly on the nuclear science. But as the time goes, we have developed various other facilities, and the name comes as an Inter-University Accelerator Center around in September 2005. We are operational for 24/7 all for all the days. So basically, so our mission is to provide front-ranking accelerator-based research facilities to create possibility for internationally competitive research within the university system in the focus area of nuclear physics, material science, atomic and molecular physics, radiation biology, as well as geochronology. Geochronology is the latest added field in our facility, but the nuclear physics, material science, atomic and molecular radiation biology, these fields are from the 91 itself. So basically what we will do, we have different accelerators having energy in the range of few EVs to hundreds of MeV. We decide the application, we decide the requirement, and we work on that accelerator facility. So basically, and we support the university system. So basically my talk will cover how one university person, either he is a PhD, MSc student, or BSc student or PhD students, how he or she can use the IUC facilities and what are the facility available for the users in all these areas. So I will cover all for those. So who can use the IUC facilities? Any research scholar, if faculty, scientist, or scientist from any university, college, IIT, NIT, any from India as well as abroad. They can use our facilities. We are having research programs using ion beams in the energy of few tens of kV to few hundreds of MeV. Basically, this range is not covered by a single accelerator. We have 5 accelerators, which some covers range in the range of kV, some covers in MeV, some covers mixture of both. But decides upon the application and requirement, we do accordingly. And we have experimental facilities for them in material science, nuclear physics, atomic molecular physics, radiation biology, EMS, health physics, as well as in geochronology. But the question is how one can apply for the these facilities and how he or she will get the beam time. That I will cover in this particular presentation. So if I cover our user distribution, so if you see this particular map, we are covering almost all the parts of our India. We are covering basically universities also, we are covering colleges also, we are also covering the research institutes, and till November 2022 we are covering more than 150 universities, 138 research institute, as well as 84 colleges. So we are working for all. Our mandate is working for all. So basically, what are the roles and responsibilities? So IAC, basically the role of the IAC is the all accelerators should be operational over the all 24/7. Basically helps in formulating research program and facilitating using users experiments. Basically what we will do is, once suppose somebody puts a proposal, so what we will do, we will help in formulating their research programs, as well as once they comes for the experiments, we serve them as a local experimental coordinator called as LEC. So we'll provide all the facilities related to the required experiments, as well as we also build new accelerator and experimental facilities needed for the further experiments or as well as for advanced experiments. So what are the various programs which are conducted by the IUCs? IUC conducts its PhD teaching program. Basically, as we have seen in last, I have seen in last 10 years, many universities are not having PhD teaching programs. So one that they can approach IUC to have to join its PhD program. Apart from that, IUC has its own research program also, where the degree is awarded from JNU. We have orientation program for the MSc students. We have summer projects for the BSc students. We have organized various seminars, conferences, and workshops to help the user, to help the scientific community. And we also do the various accountants program for the new users, because we have seen that there are many areas. If you see this particular graph, there are many areas which are still left, which are so what we will do, we go there, give our representation that we support the users, we support the universities, and how what type of programs we have. We conduct some seminar workshop there and try to have some users from there. So basically our motto is to cover all over India to help the university users or university systems. So how one can help university user, or how one can know which program is conducted at what time and how from which facility or from which department it is. So what we will do, every year we publish one document which is called as a calendar of events. If you go at the IUC website, at the bottom there is a section called as a calendar of events. In every year, what are the activities at IUC will take place, those are mentions there. So if you see academic calendar of 2024. So if you see in January, we had accountants program at Central Institute of Tamil Nadu. Suppose somebody means want to join PhD program of IUC, so it is starting from February. It is currently going on. Similarly, if you see, there is a 2 days workshop on geochronology. So suppose somebody is working in the geochronology, he wants to have some experience on geochronology facilities and something, he or she can apply this particular workshop. Similarly, if somebody is having interest in nuclear physics, so we have workshop on physics and recoil separators, which is scheduled in May 21 to 22. So if you see, we are covering geochronology, here we are covering nuclear physics. Similarly, suppose if somebody wants to perform some experiment using computational physics, so we are conducting schools on high performance computing also. So basically, if some BSc student wants to come to the IUC and see how the IUC facilities are working and wants to work on the IUC facilities as well as their own accelerators, so he or she can apply in IUC BSc summer training program, which is conducted during 3rd June to 28th June, and he or she apply can for this summer program. Similarly, every you see in July 4 to 7 we have user presentations. Basically, suppose somebody wants to apply for the beam time, so he or she can give their presentations there. Suppose in somebody is working in the field of material science for the energy storage materials, so he or she can attend this particular workshop scheduled during the in month of August. And similarly, if somebody is having interest in artificial intelligence and machine learning, they can contact this particular person. So he is also conducting some similar workshop. And suppose somebody is working in the field of material science, where one is interested in microscopy or irradiation, we are conducting one conference as well as one school in December. So what I mean to say is, basically our calendar of events is contain all the workshop, accountants program, summer projects, meetings, whatever it is in our in the one document. It is available on the website. So what somebody can see this particular documents and apply accordingly in that particular time frame. So if I go for the PhD teaching program, we have 2 semesters, semester 1 and semester 2. In semester first, which is generally scheduled during September to December, we taught advanced classical and quantum mechanics, experimental physics, as well as the accelerator physics. While in semester second, which is generally scheduled February to May, we taught advanced condensed matter physics, advanced nuclear physics, as well as computational techniques. The important part is that we ask various university users to come for this PhD training program, and the minimum required qualification is the MSc Physics. And we also provide some financial assistance in the form of travel as well as free accommodation. So the who joins these PhD training programs, we provide free accommodation, free food, as well as support for the travel. So basically, because there are many university users, we have seen they are not means getting any financial assistance, but they want to join this type of programs. So to support them, we have this particular facility. So it is again, this schedule is also available on our website. So you can contact our PhD program coordinator on this particular email if you are interested in any of the PhD program. Suppose somebody is interested in working in the field of material science and somebody wants to take the advantage of experimental technique. What are the experimental techniques generally used for the in solid state physics research? So basically, this course is also taught by me during this period of May 5th to May 30th. So he or she can apply for this particular course on this particular email ID, and the free accommodation, free travel support, as well as free hospitality will be provided for the users. So basically, apart from that, suppose somebody wants to perform a PhD and suppose somebody wants to have postdoc positions at IUC. So for PhD, CSIR or UGC NET, GRF is compulsory basically. So GRF is compulsory. We advertise twice a year, and select for a via walk-in interview mode. And we work in various fields like nuclear physics, material science, atomic and molecular physics, radiation biology, as well as on the accelerator physics. And our degrees are awarded from the JNU. And suppose somebody wants postdoctoral positions at IUC, so if somebody has submitted or awarded, he or she can apply for the postdoc positions. And we also take young scientists, national and PDFs, as well as Inspire Fellows. And we publish more than 160 research publication every year from these department or from these subjects. So as I covered earlier, we have MSc orientation program, which is basically mainly for MSc physics and geology students. So what we will do, it is generally a 3-week long MSc orientation program to encourage MSc students to supplement their knowledge and motivate them to continue their career in science. Basically, what we will do, suppose somebody applies, we will assign one scientist or engineer with them, and they works with them for 3 weeks. They do some hands-on training parts as well as some research problem. At the end, they have to submit a report, and to support them, we provide TA for sleeper class as well as free loading and boarding for the MSc students. So basically, this helps the MSc students to continue their career in science as well as hands-on experiments in the field of accelerator and their associated facilities. Similarly, if somebody is in BSc and wants to join IUSc, or means want to have some work in IUC, so they can apply in 4-week summer project, which is conducted in month of June every year. For basically, it is generally for those who want to keep their high studies in experimental physics. So basically, again, in this will we assign each student with their some faculty. They work in their respective labs and have some hands-on training with various type of systems. So at the end, they have to make a very short presentation to share their work, to what they have done and what they have learned with others. And we also provide TA for them as well as the free loading and boarding facility. And for the further details, you can visit our website. And as mentioned previous, we also do a contents program. Basically, it is with the accelerators and experimental facilities. We generally do 4 acquaintance programs in once a year, and the preference is given from those universities or institutes where very less users are coming to the IUC. Basically, so what we will do, we go to that university, college or institute. We basically have one workshop, how accelerator can promote the science and how accelerator based research facilities are performed at IUC and how IUC is helping to the users. So basically, we do 1-day workshop there to attract or to have benefits for that university or institute. So as you have seen, we have various accelerators and we support accelerator based research in various fields. So the important point is what type of accelerators we have, what are the range they are covering, and what are the fields they are in, what are the fields there these accelerators are used, and how these experimental facilities are supported by the accelerators. So I will the remaining part will cover what type of accelerator in IUC, how the beam is accelerated using the accelerators, and how the accelerated beam or is used for the experimental purposes. So first, what type of ion accelerators at IUC? So basically, we have mainly 3 type of accelerators at IUC. I at IUAC. One is tandem, which is called tandem 1D graph accelerators. Another class is the RF accelerator, and the third class is the low energy accelerators. So in the tandem, basically these are the called as DC accelerators. We have three. We have 15 UD pelletron, which is the main accelerator of the IVC, as well as we have 1.7 MV accelerator, which is generally used for ion beam analysis, like Rutherford backscattering. Similarly, we have 1.500 kV pelletron accelerator, generally used for the EMS. The full form is accelerator mass spectrometry, generally used for the carbon, beryllium, and aluminum dating. Similarly, we have two RF accelerators. One is superconducting linear accelerators. Basically, suppose pelletron is providing this 15 UD pelletron accelerator is providing some energy, but for your experiment you still need some higher energy. So that part is done by using this particular linear accelerator. Apart from that, we have SCI, which name is high current injector, because the problem with this pelletron DC accelerator and with the linear is the current is very low, but SCI the current is very high. So suppose as I proceed further, the duration of the experiments also depends upon the current. So if the current is high, you can get higher data or higher statistics in a lesser time. So for that, there is a need of high current injector. We are working on them. Apart from that, suppose somebody wants to have low energy for their application. So we have three low energy accelerator. One is positive ion base, which is called positive ion beam facility. The ion source is ECR base. Another is the negative ion beam facility, which is MC SNICS base. The full form is multi-cathode source of cesium ions by cesium source of negative ions by cesium sputtering. SNICN means source of negative ions by cesium sputtering, and MC means multi-cathode. Why it is multi-cathode? Because we can load 40 cathode at a time. Means suppose today somebody wants a beam of aluminum, tomorrow he wants iron, so you need not to change the cathode at a time. You can load 40 cathodes at a time and you can select accordingly and tune your beam. And we are having a tabletop accelerator where we takes energy in few kVs. This positive ion beam facility covers energy means 1 kV to MeV. The negative ion beam facility covers energy up to 200 kV, while tabletop ion accelerator covers energy in the range of tens of kV. So if I summarize, this is our all accelerator facilities. It is over 15 unit double pelletron, and it is over a combination of with the superconducting LINAC, and these are the 1, 2, 3 LINAC modules where we further accelerate our ion beam. It is our RBS facilities where 1.7 MV tandem accelerator is available there. Apart from that, this is our AMS facility. This is MC SNICS negative ion beam facility. It is positive ion beam facility, and this is 500 kV tabletop accelerator system. And this system can also be used at the universities. At it is I think less than 20 lakhs in less than 20 lakh rupees you can build this particular accelerator. So it is a tabletop accelerator which can use in any place at any institute. So our main accelerator is basically the pelletron accelerator, which is having a structure like this. So basically it is a 8th floor building where at the top we have ion source room. Inside we have which produce the negative ions. We have various type of magnets, then buncher, and these are the various parts of this particular accelerator. Then here we have analyzing magnet where we select a particular ion. Then here we are having a switching magnet. So because in this magnet helps in which beamline. If you see here 1, 2, 3, 4, 5, 6, 7, we have 7 beam lines. So basically one is for boosting the energy, it is going to the linear. Another 6 are the experimental lines related to the radiation biology, atomic physics, HIRA, metal science, GDA, and GPSC. Basically, scattering chamber is GPSC, called as GPSC, general purpose scattering chamber. So these are the various beam lines. So basically, it is our Peloton is our. If I discuss in detail, this is our DC accelerator, which is having height of 26.5 meter with a diameter of 5.5. And if you know, if I have shown you the terminal voltage or the TP is 16 million volts. So here this is the terminal voltage. So if you have 16 million volts, so it is very high voltage. So there is a chances for breakdown. So what we will do, we put SF6 around of this. So the pressure of that SF6 is maintained around 19 psi. And what type of ions are accelerated? We can accelerate all the ions from hydrogen to gold except inert gases. Why inert gases are? Because as you have seen in the this particular slide, it is also using multi-cathode Sneaks ion source, and with Sneaks ion source we cannot produce a negative ion, so that's why we cannot use inert gases to accelerate. And the typical ion current is 5 to 50 particle nanoampere, covering the range of energy 30 to 250 MeV. So in this particular slide, I will cover how a particular ion is accelerated and how it is sent to the various beam lines and how the experiments are performed. So basically, if you see the geometry, it is our ion source which produces the negative ion. How the negative ions are produced, that I will come in next slides. Okay, so it is our Sneaks ion source which produces the negative ion. So once these negative ion produced, they are accelerated due to the basically called as ion source voltage, which is of the order of 200 kV. It repels. Once these ions reaches here, using this injector magnet, we select, we bend basically these negative ions. How this magnet bend? As you all know, QV cross B equal to MV square by R. So basically, we know the charge state Q, we know the velocity because the energy is QV. So from that we can calculate Q, and B, you know the magnetic field. So M, you know the basically the ions which are taking. So you can bend those ions. So here this particular point is having that positive potential of this 15 MV. So what happens when these ions bend by this injector magnet? These are attracted. So what happens? They gains the energy. How much energy? Energy gain is Q cross V, and this V is of the order of million volt. So the energy gain in the upper section is Q cross V, where V is in the million volts. So energy at this particular point is in million volts. So when these ions attract towards this particular terminal potential, these ions are passed through the carbon foil or the nitrogen gas. So what happens once these ions passes through the carbon foil? The charge exchange phenomena happens, and these negative ions basically eject their electrons and become positive. So once these ions become positive, they are further repelled, because suppose it is positive. Since it is positive, the negative ion will attract, and once these ions become positive, they will repel. So what you are doing is, using the same terminal potential, you are having double acceleration. One is from the attraction and another is from the repulsion. That's why this is called 15 UD. 15, since the TP is 15 and UD means unit double, means you are getting acceleration twice from a single potential. So once this energy is once these ions pass through this TP, they gain some energy. The energy is of the charge state of their ion. So since this is negative -1 and their charge state suppose Q, so the energy gain is Q plus 1. 1 is from negative side and Q is the positive charge on the ion and V is the million volt. So the total energy which is ions at this particular point is Q1 plus V. And again, using the analyzer magnet, we select the particular ion because there is a possibility that suppose take a practical example. Suppose you are accelerating silver. So once these silver ions, the negative silver ions are coming, they are attracting at this particular points. Once it become Ag plus, it is not necessarily that it will be only Ag plus. There will be Ag plus 1, plus 2, Ag plus 3, Ag plus 4. All the possibilities are there. So depending upon the energy requirement, we select the appropriate ion or proper ion using this analyzer magnet. So only the particular energy is proceed further, and once it reaches this particular point in which beamline we need experiment or in which beamline we need energy, we provide certain magnetic field and band or this ion beam in a particular beam line. So basically I am working in the material science department, so it is basically 15 degree beam line. This linear is called as 0 degree beam line. This is plus 15 degree and it only IRA is the minus 15 degree line. So they put some magnetic field to bend these ions to have necessary experiment in a particular beam line. So suppose if, as I seen in previous slide, the energy is Q1 plus 1 into V, where Q is the charge state of ion. If I take the practical example, suppose we take the example of oxygen. Suppose in this particular stage it is in Q6 plus, and suppose over terminal potential 12.5. So energy gain is 6 plus 1 7 multiplied by 12.5 comes around 87.5 MeV. Similarly, if you take the example of silver, where suppose considering the charge state of 9 plus and same TP, the 9 plus 1 10, the energy is 125 MeV, and the generally current produced this peloton accelerator is of the order of 2 to 3 PNA. PNA basically is the particle nanoampere. The particle nanoampere is unit to measure a normalized current. So basically, what is the PNA? PNA is the total current divided by its charge state. So it is a normalized current. Okay. So as you have seen this particular accelerator, so we produce the negative ions. So how these negative ions are produced? So this is explained in this particular slide. So basically, at the top, at the 7th floor, we have our ion source, and how this ion source looks like. So basically, this is the geometry of the ion source, and if you see, there is a high voltage ceramics are there, and we applied around 200 kV voltage at these ceramics. So basically, this deck is RC at 200 kV, and it is, if you see this, we have 40 cathodes. So that's why the name is MC, means multi cathode. So where we can load 40 cathodes at a time, and SNX, source of SNX, as the name is, source of negative ions by cesium spectrum. So basically, what we will do, we have a heater here, and we have our cathode from where we want to take some beam. So what will happen, we have this oven there. So once we heat this oven, some cesium ions will deposit over this particular sample, and using this sputtering technique, we take out the required ion beam. Basically, what will do, these cesium ions will go to the cathode and they'll take out them and will take out these negative ions, and these sorry, the cesium ions go to the cathode and produce the negative ions, and these negative ions are taken out using this extractor. This is a basically particular geometry which is holding 10 to 15 kV voltage. So basically what it will do, it will extract the negative ion produced using this cathode. Okay, and these negative ions then further accelerated as explained in these two slides. So as you have seen, the total energy is obtained using the peloton is up to 250 MeV. But suppose somebody wants some experiments at some higher energies, for that what we will do, we go for the linear accelerators. So this type of geometry you people might have seen. It is a general geometry of the linear accelerator where we have different drift tubes having certain lengths, and the length of the drift tube will depend upon the velocity of the injector ions. So if you see, the length of the drift tube is increasing because as you go from one drift tube to the another, because of the having some applied electric field between them, the energy will increase. So as the energy increases, the length should be increased too, so that the ion is continuously facing the same electric field once it's come out through the drift. So if I do a combined layout of our accelerator, it is our pelotron, then it is our switcher magnet. So it is our 0-degree beam line where we inject our beam from pelotron to the linac, and these are our 3 linac modules, in which in each module we have 8 cavities, and these are the again rebuncher. Then we have again these 4 beam lines to have experiments at higher energies. So suppose these are some examples where suppose somebody wants some experiments in NAND. So he or she wants the total energy is 300 MeV. So what we have done is we are providing 160 from peloton and 132 from the linac. So what we will do, if you see, the linac boost our energies up to 60-70%. Even sometimes it is up to the 80% also. So it helps, linear accelerator helps our experiments in the high energies. So these tandem and basically linear accelerator are the higher energy accelerator. But suppose somebody wants to work at low energy, suppose somebody wants to do some implantation type of work. So for that we have 3 low energy accelerators. One is ECR based, basically which is low ACR based, basically it is basically a positive ion beam facility in which we have 3 beam lines. 2 are material science and atomic and molecular physics, and third one is basically for the highly charged ions, where we can have energy almost nearly zero, which we also called as soft landing setup. Suppose it is generally useful for those people who are working on 2D materials. Suppose somebody is working on 2D material and he want to attach some molecule or some ion to its surface. So they can use over this soft landing setup at low energy ion beam facility, and they can characterize their samples later on to get what is happens or what is the physical changes once this some molecule or some atom is attached to a 2D material. Suppose similarly somebody wants to perform implantation studies up to 200 kV. We have negative ion beam facility where currents of the order of 100 to tens of microamperes are provided, and again the source is since SNICs, so again we can load up to 40 cathode at a time, and we can have all the ion beam except inert gases. and it is generally used for implantation studies in insulator, ceramic, or single crystal type of samples. And the third accelerator in the low energy range is double tape accelerator, and if you see its physical size is 1.6 cross 1.4 cross 1.5, all are in meters, and it is generally used for the low energy implantation and induced fluorescence at low energy experiments, low energy scattering experiments. And if you see the physical side, it is very less, and the total cost for to making this accelerator comes below 20-25 lakhs. So some every university or college can have these accelerators at their places to have some experiment related with the accelerator for their students. So comes to the as in the first section we have covered the general programs offered by UAC. In second part we have covered the type of accelerators at IUC. In part third, I will cover what are the research program at IUC. So basically, we generally cover 6 areas: with nuclear physics, metal science, radiation biology, accelerator mass spectrometry, atomic physics, and health physics. So I will cover each of them. So basically, if I talk metal science, so what we will do, we play with the energetic ions, and what these energetic ions do. These energetic ions provides various type of effects over material, and depending upon the type of requirement we can use them. So if I want to synthesize some materials using ion beam, we can use implantation, nano patterning, or ion beam sputtering type of studies. Suppose if I want to characterize our material, so we can use RBS, ERDA, QMA. Suppose I want to modify or tailor its material properties, we can use nucleation, amorphization, phase transformation type of studies. So if these basically, if you see this particular slide, the energy decides what type of application. Suppose if you want to synthesize some material, so what you can do, you want energy in the EV2 few kV. Suppose you want to have some implantation, you want energy in the tens of kV to tens of MeV. Suppose you want to have metals modification, so if energy is less than MeV, this Sn is dominating. If the energy is greater than 10 MeV, Se will dominate. Basically, Se and Sn is what? Sn is the nuclear stopping power, and Se is the electronic stopping power. So basically, these are the two effects which generally modifies the material property depending upon the energy. And this accelerator also used for the materials characterization. Suppose if the energy is few eV, we can use in RBS or ERDA or PIXI or NRA, and if energy is of hundreds of MeV, this is a high intensity ERDA experiment. So depending upon the energy, we can have various type of metal science experiments. So coming to the IUC metal science facilities, basically it is over peloton. After that, these are the 7 beam lines. It is over material science facility where we perform the irradiation chamber, this one, and this one is the GPSC, where we can perform low Fulvex, or basically low Fulvex irradiation. Because if suppose somebody, our peloton provides an beam current in nanoampere, 10⁻⁹, but suppose somebody wants to perform experiment at 10⁻⁷ or 10⁸ flex, so they can use this particular setup. And this particular combined area is called as beam hole 1. After that, we have lean neck. This is proceed further. This is metal science beam line in beam hole 2, where first we have in situ Raman, then we have irradiation chamber. This chamber is also used for the irradiation as well as high temperature studies, and at the last we have in situ XRD. So these are the some photographs of beam hole 1. This is basically our irradiation chamber. It is the top view, and it is the side view of that particular chamber where we perform the irradiation experiments. And it is the hydraulic lift to have automatic up and down movement of our samples during irradiation time. And these are the some facilities in these are the facilities are in beam hole 1, and these are the facilities in beam hole 2. We have in situ XRD, we have in situ Raman, and we have irradiation chamber which can operate at high temperature up to 1000 degree. So the basically the advantage of the in situ studies is, from these type of studies we can avoid sample to sample variation, and it will take lesser time. If you compare the total study time, you can perform all the fluence. If you start from 10 power 10 to, suppose if you want to go 10 power 14, you can complete all the studies on a single sample using these particular setup. And suppose somebody want to irradiated his or her samples at higher temperature and want to see the temperature dependent effects on the irradiated sample, they can use this particular facility in material science beam hole 2nd. Apart from that, in material science we have various offline facilities, like for electrical transport we have FTIR, we have PL, we have scanning electron microscope, we have scanning probe microscope, we have TM newly installed from Geol. It is of energy 200 kV, as well as UV visible and contact angle setup. So these are the some online and offline facilities of the material science group. Now we will come to the nuclear physics research at IUC. Basically, in nuclear physics we have basically two broad areas. One is reaction and another is the structure. So there is one group, basically those who are working on the nuclear reaction, and another group, they are working on the nuclear structure. So in nuclear reaction we have four sub facilities. One is heavy ion reaction analyzer, another is hybrid recoil mass analyzer, third one is the general purpose scattering chamber, and fourth one is the national area of neutron detectors. And for the structure type of studies, we have GDA as well as INGA. So basically this INGA is Indian National Gamma Array, and it is the combined facility of IUAC, VCC Kolkata and some institute, some another institute. So what it happens is, these facility remains 2 to 3 years at IUC, then another institute, then another institute, then again comes to the IUC. And all these, apart from these 4 and these 5, these facility are the permanent facilities of IUC, which are always available to the user at any time. So if you see HIRA and HERA, these are the experimental facilities. This HIRA is situated in beam hole 1, while this HIRA is situated in beam hole 2 of the IUC. So where we can produce fusion and fission type of dynamics studies in these two facilities. If suppose somebody wants to do its reaction dynamics using neutrons, so we have this 360-degree distribution of various neutron detectors, and the facility name is National Array of Neutron Detectors. So basically this study is used to study the neutron dynamics or neutron multiplicity distribution, to have knowledge about complete and incomplete fusion reactions. So what we will do, we have these 360-degree distribution of the neutron detectors, and we determine the energy as well as the recoil angle of these neutron detectors of neutron using these detectors. So apart from that, for structures we have these GDA, called as Gamma Detector Array, as well as INGA, Indian National Gamma Array, to have various experiments on nuclear structure type of studies. So generally what we will do is, suppose some nuclear reaction is happening. So what we will do, what type of reaction is happening. So the reaction people will do, and once the reaction happens, some excited nuclei will form. So what is its structure and what are the subparticle it is emitting? Those are studied using GDA and INGA. So as I mentioned in earlier third or fourth slide, somebody from university, research institute, faculty, students, anybody can use the IUC facilities. So how one can use? So there is a procedure for that. The procedure is to avail the accelerator beam time. One must submit beam time proposal by online filling the BTR form, which is BTR means beam time request form, within the mentioned dates. The general date is 15 May for July AUC and 15 October for the December AUC. Basically, what is AUC? This AUC is Accelerator User Committee. We generally evaluates your proposal, and you have to present your research problem in the front of AUC. And once they finds that yes, your problem is unique, there is some physics can be done, or it is very interesting for the user community, they will provide the required beam time. So for that, you have to apply online, and the duration is it should be up to 15 May. For July, suppose somebody wants to have beam time presentation in July, they have to submit their proposal by 15th May. And suppose somebody wants to have presentations in December, they have to present their proposals or submit their beam time request form by October 15. After that, once they are beam time forms are submitted, they have to present their work in front of Accelerator User Committee, which is fixed July 5 to 7 and December 16 to 18. And for further details, how to fill, how to get the beam time, you can visit our website. And the one important thing is, suppose you are putting some proposal. Okay, first I will cover this slide, then I will come to this. So there are various categories. Suppose if you see here BTR1, if you see here BTR2, then again BTR3, then you have BTR4 also, and we have BTR5 also. So what are these, and what are the conditions of getting these beam time? I will explain little. So basically, what is BTR1? BTR1 is a beam time request which can be proposed by any means it can be from any faculty or any student or any collaborator. So suppose somebody wants to have beam time for its experiments or its physics problem, they can present BTR1, and it can be presented by any collaborator, any PI or its student. But suppose some students want to have experiments using ion beam and wants it as a thesis proposal, then he or she needs to fill BTR2 form, and in that case only students has to present, and the guide has to may present during the meeting, but student has to make its presentation, and this will account as their BTR2, and it will goes into the thesis of the student. Suppose there are some faculties in various university or colleges, they want some beam time experiments with some funding, so that they can hire some students who he or she can work in that particular project. They can fill BTR3 form. So in that case, we provide the contingencies as well as the fellowship to the students. So for the BTR3, only the PI of the project should present the BTR. Basically, present the presentation in front of IUC. Students are not allowed. So, and suppose if you got the beam time, but the shifts are not sufficient. In that case, what you can do, you can submit BTR form, and for that presentations are not required. The BTR4 form will be evaluated by the AUC, and the extension of the beam time will be provided. And suppose somebody wants some experiments with the low energy. So they need to submit BTR5, and for that PI or any student or any collaborator can present that work in front of IAC. So for low energy, you need BTR5. And suppose somebody needs funding for the funding as well as low energy beam. So for that, you have to fill the BTR5 as well as the BTR3 form, and it has to be presented by the PI only. And if you want low energy without any funds, so then you can present BTR5 with BTR1. So these are the requests. For that you can have your beam time request. Apart from that, you can apply for the offline facility utilization. So suppose if you want to have you want to have some utilization of metal science facility, you can apply using this particular link. Suppose if you want to have some facility related to the geochronology, you can apply this particular website. And suppose if you want to prepare some samples for your geochronology related work, so you can apply using these two links. So basically what we will do, we provide access to the user for our online as well as the offline facilities. And for that, for the beam time request, you can apply using these BTR form, and for the offline facilities you can apply using these forms. But the condition for applying for offline facilities, you must have beam time account in IUC. We generally provide the facility utilization only the users which are having beam time account in IUC. So it is my last slide. So the conclusion of the talk is basically IUC is one solution for your stop solution for all your ion based research activities. We provide ion beam of various types, energies, as well as the various current, helps in characterization of various facilities online and whether it's offline. Every user is coming from every university, college, students, academician working in the relevant fields are always welcome, and we provide users support as maximum as we can. Thank you for your kind attention.
Thank you so much, Meena sir. It was a wonderful presentation by you. Now, sir, can we have a few questions?
Yes, definitely.
Spectators can have their questions either in the chat box or can directly ask it to the sir.
Actually, ma'am, basically the mandate of IUAC, as I mentioning it again, to help the university users. So basically, what we do is we promote the various users coming, because I have seen in last 10 years there are many university, many institute where the people are not having even simple furnaces also. Especially such type of facilities are lacking. So we generally support all the university users to boost their research activity or promote their research activity. So you are all the peoples are welcome.
Yes.
So
if there are no questions, if there are any questions, you can also write it to the university mail or sir's mail ID. It's there in the sir, can you please mention your
Yes, I will share.
Yeah.
Is my slides are visible?
Yes, sir.
So you can note down. Yes, this one. It is available on the website also.
Yes. Now, moving ahead, I would request one of my fellow labmate, Mayur Parmar, to kindly deliver the vote of thanks. Mayur, over to you.
Am I audible? Hello.
Yes, you are.
Yes. Good evening, everyone present here. Myself, Mayur Parmar. On behalf of Vigyan Yatra, I am here to give vote of thanks. Firstly, I would like to thank both invited speakers First, Dr. Sudhindra Raipol, who give the brief and informative information regarding neutron diffraction, which can be further useful for the material characterization. And second, I would like to thank Mr. Ramcharan Meena sir, who give the informative information about the IUC facilities and programs. I would also like to thank Professor H.O. Jetwa sir for chairing the session. It is my pleasure to thank our chief patron, Professor Nilabari Ben Dave ma'am, Dr. Arvind Ranade sir. Our patrons, Professor Chaitanya Joshi sir, Professor Girish Bhimani sir, and Dr. Narottam Sahu sir. Our co-patron, Dr. R.J. Parmar sir, and Sri Jignesh Borisagar sir. I would also like to thank our convener of GVS 2024, Rajkot, Professor N.A. Shah sir, and Professor P.N. Joshi sir. Our event coordinators, Professor J. Bhalodia sir and Dr. David Dhruv sir. Apart from this, I would also like very thankful to Vigyan Gurjari and GUJCOST for managing the conference series, and I would also like to thank for all the participants to present over here. I would also like to thank press media for wider publicity and outreach. Okay, from now we are ending the Pradesh session. Tomorrow
Mayur.
we will meet at the same time.
Mayur, actually there were, I was reading the chat box, there were two questions. One is from Mehul Parmar.
Yeah.
She's available now? Mehul?
Yes, sir.
Mehul, actually you have asked what are the facilities available for the electrical transport. Correct? So the facilities available are resistivity, dielectric, IV, Hall effect, and Seebeck effect. These are the 5-6 facilities, as well as the AC susceptibility, and all these facilities are temperature dependent, where you can perform experiments in the from 10 Kelvin to 450 Kelvin or 500 Kelvin. As well as you can perform in situ experiments also. Basically, you can perform in situ resistivity, in situ IV type of experiments in our IUC. You can check suppose if you are working on the devices, we also perform the in situ experiments on the devices also. Since I is looking for the passport lab only in IUC, so basically I have
One more question, sir. I have. Hello.
Okay, so if you need, if you want to use any of the facility related to
Meena, sir, I have one more question to ask you. Do you have thermoelectric power?
Pharaoh? Mayur, can you?
Thermoelectric power, sir.
Thermoelectric power, yes, we have.
Yeah, is it clear, Mehul?
Yes, okay, sir. Thank you, Meena, sir, for giving us such a good answer.
Okay, thank you very much, Meena, sir.
Thank you.
Okay.
Bye.
Then.
Okay, so we end the session for today. Now I request all the spectators to kindly rejoin tomorrow again on the same time and same platform. Thank you all.
Thank you.